So the reason some of our groups in our periodic table have a name is because every element in that column has similar properties. And in general, every single column, the elements within it have similar properties. It's just that like some of these groups have extra interesting ones and they kind of earn some a name. And so I've listed them here in a table and like this is for your information sort of thing. This isn't something to memorize. And I think the things that are the most interesting in it are that your alkali metals are very reactive, except for hydrogen. And by very reactive, we do mean that they explode. So think about if you've ever seen a sodium metal and water reaction. If not, I will link it as well. But you can take a piece of sodium metal and it reacts so vigorously with water that it catches on fire. So you'll just see this metal on fire dancing on the surface of water, and it's just so cool. Our halogens are also one that I always kind of think of a lot because they're around. They're also pretty reactive, and they're always diatomic molecules. So that means that when they're in an elemental state, so that means just bromine on its own being a bromine element would always be found as Br2, and it's just that they form a bond with one another as an element. Other things that are really interesting in terms of like unique properties is that the noble gases are basically inert. And so that means that they just don't react with anything. Some of the heavier ones lower down on the periodic table, they'll react in kind of special limited situations. And these are going to be gases that are just one atom floating around. So it's pretty interesting. The transition metals also form lots of different types of ions. It's kind of their superpower, which is interesting. So I use this only to point out that we see these trends in like how they elements in the same group behave. And that really comes from these elements having the same number of electrons in their outer sphere or outer electrons. These are the electrons in an element or an atom that are the furthest away from the nucleus. And they're the ones that are kind of that last barrier between the atom existing and then it just being space. And that means they're the electrons that interact with the environment and with other atoms that are around it. And so they really dictate the behavior of each of these elements. And so the unique thing about them is that the groups of our periodic table all have the same number of outer electrons. And that's why we see similar behavior, because the part of the atom that is interacting with other atoms has the same number of electrons in it. So it's going to behave similarly. So let's talk about what these outer electrons are and kind of think a little bit more about the structure of an atom. And so we had talked about it before. We're like, there's this nucleus. It's tiny, but it's heavy. And then there's all this space that's large and has a lot of volume, but has very little mass. And that volume is occupied by these electrons. That's why it has so little mass. So within that, the atom will actually organize the electrons in a way that gives them actually different amounts of energy, right? And the further away they are from the nucleus, the higher energy they will have. They're just like further away, so it's not as strong of an attraction between the negative charge of the electron and the positive charge of the nucleus. So like as they get further and further away, that attraction gets smaller and smaller, that attractive force. Kind of like when you have two magnets and they're far away and you're like, I can hold these just fine. But as you bring them close together, they grab each other. So our electrons, we could determine what the outer sphere ones are by determining something called an electron configuration. We're not going to go into that level of depth. And I'm just going to show it an example here and then show you how you can determine this without knowing where every electron in an atom is, which would be a bit of work. So my example here is carbon. So carbon has 6 protons. And as an element, it would then have 6 electrons. Now, the first 2 electrons are right here, 1 and 2. So it has these 6 electrons are kind of organized as 2 are closer to the nucleus and 4 are further away. And so those 2 that are closer, we think of as inner or core electrons. And then they have 4 outer electrons. And so these 4 outer electrons, these are our valence electrons or outer electrons. You can call them either one. And they're right here. And so there's just 4 electrons that are interacting with the outside world of this atom. And we can see in the periodic table then that each group has the same number of valence electrons when we look at the electron configuration for each one. Which we won't do. I'm going to just jump to the kind of punchline and show you what the number is for each. And so everything in the first column, all of these elements have 1 valence electron. So this will be the number of valence electrons. And I'm going to revise this statement of each group. It's really each group in the main group elements. The transition metals and the lanthanides and actinides kind of do their own thing. So the second column or group has 2 valence electrons each. We're going to skip the transition metals, and then we come back to our representative elements or our main group elements. And everything in this third column that we're looking at has 3 valence electrons or 3 outer electrons, and then 4, and then 5, 6, 7, and 8. So if it's in one of these columns or one of these groups, you know exactly how many valence electrons it has or how many outer electrons it has. Sorry, I'll jump between those 2 words because they mean the same thing. And so because of that, with all of these like 8 electrons for each of the noble gases in their outer sphere or their outer electrons, they're all going to behave really similarly. That inertness comes from that 8 electrons. And so this is important because we're going to use an element's outer electron count to help us determine how many bonds it will form if it forms a molecule or how it will make compounds, like if it will gain or lose electrons. And so that valence electron or outer electron number for each element will allow us to predict its behavior ultimately. And it will also help us determine its shape and understand a lot more about the molecules that it would form. So we'll come back and use that number a lot. So it's important to remember or have written down on your periodic table the number of valence electrons that each grouping has of our main group elements.